Welcome to the deep dive. Okay, just look around you for a second. You might see a bird zip past the window. Maybe your phone is just sitting there perfectly still on the desk. A car outside kind of gliding by. The world is just, brimming with movement and stillness. Yeah. We think we know what motion is, what at rest means. Pretty basic stuff. But what if those ideas are, well, far more slippery and maybe even mind-bending than we ever imagined? Today, we're doing a deep dive into the fundamental concepts of motion and rest. And they can be surprisingly nuanced. We've got an insightful stack of material here, including a core physics chapter that's going to guide us. Our mission really is to unpack the definitions, explore this kind of shocking relativity of motion, classify all the different ways objects can move, and even clear up some classic confusions, like the difference between mass and weight. It might actually change how you see the world around you.
Yeah, what's really fascinating here is how these foundational ideas, they seem so basic, right? But they actually shape our entire understanding of the physical world and, how often our everyday assumptions, like about being still, can be, well, profoundly challenged by what we're about to get into.
Okay, so let's start right at the beginning. The absolute ground floor. What exactly is motion? And what does it truly mean for something to be at rest? I think we all have a gut feeling, an intuitive grasp. The material we looked at gives us a really precise way to think about it.
That's right. Motion, at its core, is simply a change in an object's position over time. Simple enough. But there's a really crucial piece. It's always with respect to a fixed point in its surroundings. That's key. So that bird flying past your window, it's changing its position relative to, say, the tree outside or your house. That's the motion we see.
Ah, okay. So motion is about that shifting position relative to something else. That relativity is built right in. And then being at rest must just be the opposite. No change relative to that fixed point.
Precisely. An object is at rest if its position doesn't change relative to a fixed point in its surroundings. Like, think of that book on your table again. It stays put, relative to the table anyway, unless, something moves it. It truly boils down to that chosen reference point. Yeah. What are you comparing it to?
But here's where it gets, well, really interesting and honestly a little bit mind-bending for me. Our deep dive shows that rest and motion aren't some absolute fixed states, like universally true.
Yeah.
They're entirely relative, which means, well, it means an object can be moving relative to one thing, but completely still relative to another at the same time. How does that work?
It's a fundamental shift in perspective, really. Consider yourself right now, maybe sitting in a room listening to this. You feel absolutely at rest, don't you? And relative to the chair you're in or the walls around you, you are stationary. That's true. But that room, your home, your city, it's all sitting on planet Earth. And Earth, as we know, is constantly spinning on its axis, and it's hurtling around the sun at like incredible speeds, thousands of kilometers per hour. So relative to the sun, you are absolutely in motion. You're on this wild ride through space. Your perception of reality, whether you're moving or still, it totally depends on your frame of reference.
Wow. Yeah, that really does bend your mind when you think about it that way. It's kind of profound, isn't it? So even when we feel completely still, we're actually on this cosmic journey. It reminds me of that classic example, like being on a bus or a train.
Exactly. That's a perfect analogy. If you're a passenger sitting on a moving bus, right? The driver probably appears to be at rest relative to you because their position isn't changing compared to where you are on the bus. But then you look out the window and all the trees, the buildings outside, they're whizzing by. They are clearly in motion relative to you, even though, they're at rest relative to the ground.
So who gets to decide then if something is at rest or in motion? Is it just arbitrary, whatever we choose to compare it to?
In essence, yeah. It really is the observer and their chosen surroundings, their chosen frame of reference. I mean, think about two trains moving side by side on parallel tracks at the exact same speed, same direction. A passenger in one train might look across and perceive the other train as being perfectly still, right, at rest. But then imagine another train going the opposite way on another track. That would appear to be moving very, very rapidly past both of them. So your observational frame of reference is absolutely everything. It's a really powerful point, especially when you apply it to just everyday life.
Okay, mind's officially open to relative motion. But even within motion itself, there's so many ways things can move. It's not just, going in a straight line, is it? Our sources actually categorize these, and it reveals this whole, symphony of movement out there. What are some of the broad types?
Yeah, when we think of motion, often the first image is just, something moving straight, A to B. But our deep dive really highlights this incredible variety. We can kind of group them broadly. You've got things that basically slide, things that spin, things that swing back and forth, and even those tiny invisible jiggles. Let's start with maybe the simplest. The sliders, or what's technically called translatory motion.
Translatory motion, okay. What does that look like in the real world? Give me an example.
So this is where an entire object moves, right? And every single point, every little bit on that object travels the exact same distance in the same amount of time. Imagine like a book sliding straight across a table, or a bicycle just moving along a perfectly straight road. The whole thing moves together. Now, even within translatory motion, we have two subtypes, rectilinear and curvilinear.
Okay, rectilinear. Rectilinear sounds like straight line. Am I close?
You got it. Rectilinear, or sometimes just called linear motion, is exactly that. Movement in a perfectly straight line. Think of a ball dropped straight down, or a car cruising on a dead straight highway. Curvilinear motion, on the other hand, is movement along a curved path. So, like a cyclist taking a turn, or maybe a ball thrown by an athlete that arcs through the air, right? That's curvilinear.
Got it. Straight path, curved path. That makes sense for the sliders. So if we've covered translatory, what's next in our motion symphony?
Next up are the spinners. This is rotatory motion. This happens when an object moves about a fixed axis. But crucially, that axis actually passes through the body itself. Think of a ceiling fan spinning around its center, or, the Earth rotating on its own axis. That axis goes right through the Earth. And a key point here is that different parts of the object move different distances in the same amount of time in rotatory motion. Like the tip of the fan blade travels a much bigger circle, moves much further than the part near the central hub, right? And the same spin.
Ah, okay. So that's different from circular motion then. Because that sounds really similar, but there must be a subtle difference.
It's a really crucial distinction, actually. In circular motion, yes, the body moves along a circular path, and its distance from a fixed point, the center of the circle, stays constant. But here's the key. The axis of revolution, the point it's going around, passes outside the body. So think of a satellite orbiting Earth. The Earth is the center outside the satellite, or the hands of a clock moving around the center point of the clock face. See the difference? Earth's rotation on its axis is rotatory. Earth's orbit around the sun is circular motion.
Okay, I see it now. It's about whether the axis is inside the object or outside, like a top spinning in place versus a dog chasing its tail around a tree.
Exactly.
Okay.
That's a great way to picture it. And yeah, understanding that difference helps us track everything from planets to satellites with incredible precision. So we've had our sliders translatory and our spinners rotatory and circular. What about those back and forth type motions?
The to and fro guys.
Yeah, those are our swingers and jigglers, kind of, more formally. Oscillatory and vibratory motions. Oscillatory motion is that classic to and fro movement of an object from its resting point, its mean position, like a pendulum swinging back and forth in a grandfather clock, or a child on a swing set. It's a regular, repetitive back and forth. Now, vibratory motion is actually a specific type of oscillatory motion. Here, part of the body usually stays fixed, and the rest moves to and fro really rapidly. And during this vibration, the body's shape and size can actually change slightly. Think of a guitar string. When you pluck it, it buzzes back and forth, or even our own vocal cords when we speak.
Whoa, fascinating. So a guitar string isn't just swinging, it's also kind of distorting its shape as it vibrates. That's cool. And then there are motions that seem to relate more to time, how often they happen.
Indeed. That brings us to periodic and non-periodic motions. Periodic motion is pretty straightforward. It's any motion that repeats itself after a regular, fixed interval of time. The Earth revolving around the sun that's periodic takes about 365 days. The moon orbiting Earth, about a month. Even your own heartbeat, hopefully, is roughly periodic. They're reliable, predictable cycles. Non-periodic motion naturally is the opposite. It's when a motion does not repeat itself at regular intervals. Like, think of a footballer running on a field, their path is unpredictable. Or a car applying brakes and slowing down in traffic. And then there's also random motion, which describes that really chaotic, zigzag, irregular movement you see sometimes, like dust motes dancing in a sunbeam, or particles and liquids and gases bumping around.
I love how our deep dive also points out mixed motion, because that feels so much more like the real world, doesn't it? Very few things only do one type of motion. Many objects actually exhibit more than one type simultaneously.
Absolutely, that's a great point. Think about the wheels of a moving car or a bicycle. As the vehicle moves forward along the road, that's translatory motion, right? The whole bike is moving. But the wheels themselves are also spinning around their axles. That's rotatory motion, happening at the same time. Or think about a carpenter's drill. It's spinning rotatory to bore the hole, but it's also advancing forward into the wood that's translatory. Even the Earth itself, as we mentioned, shows mixed motion. It rotates about its axis, rotatory. It revolves around the sun in a roughly circular path, circular. And this revolution is also periodic. It's this beautiful, complex dance of multiple motions all happening at once.
Yeah, so it's not just a list of physics terms to memorize, is it? It's really about appreciating how complex and, well, beautiful the movement around us actually is.
Yeah.
Often several types layered together. Okay, now shifting gears slightly, let's talk about something we all kind of instinctively get: speed. We know what it means to go fast or slow, but how does our source material define it precisely? What is speed, technically?
Right. Speed is basically the quantity that tells us how fast or slow an object's motion is. The standard definition is the distance traveled by the body in unit time, so how much ground you cover per second or per hour. The standard international unit, the SI unit, is meters per second, though, in everyday life we often use kilometers per hour, kilometers or miles per hour. What's really useful here is distinguishing between uniform and non-uniform motion based on speed. Uniform motion is when an object covers equal distances in equal intervals of time. Its speed remains perfectly constant. Like, imagine a car on cruise control on a perfectly straight, empty highway traveling exactly 60 miles every single hour. That's uniform. Pretty rare in reality, though.
Exactly, because reality is usually non-uniform motion, right? That's when you cover unequal distances in equal time intervals. Like a car accelerating from a stoplight, then slowing down for traffic, maybe speeding up again. Or a cyclist navigating a busy market street. Constant changes in speed. And for these real-world scenarios, which are, let's face it, most common, we need a different concept: average speed.
That's right. Average speed is the practical measure. It accounts for all those variations, the speeding up, the slowing down, the stops and starts. It's calculated pretty simply. Just the total distance traveled by the object divided by the total time taken for the entire journey. So if a car travels, say, a total of 150 kilometers and the whole trip takes 3 hours, its average speed would be 50 kilometers per hour, 150 kilometers 3h. Even if it went faster or slower at different points during those 3 hours, it kind of smooths out all the bumps, gives you the overall rate.
Yeah, it's like the bottom line for your trip, isn't it? Unless you're on that mythical, very long, very empty road, average speed is what actually tells you how fast you're really getting from A to B. Okay, finally, let's tackle a concept that often gets mixed up, even by people who think they know physics pretty well. Mass versus weight. Our sources make a really, really critical distinction here. This one's important.
Oh, absolutely. This is fundamental, and yeah, it's often misunderstood. Let's break it down. Mass. Mass is the quantity of matter contained within a body. It's the actual stuff something is made of. It's what we call an intrinsic property, meaning it's constant. It does not change no matter where you are in the universe. On Earth, on the moon, floating in deep space, your mass stays the same. It's typically measured using something like a beam balance, comparing it to known masses, and its SI unit is the kilogram. And crucially, the mass of a body can never be zero. If something exists, it has mass.
Okay, so if my mass is, say, 70 kilograms here on Earth, that means my mass is 70 kilograms absolutely everywhere. Moon, Mars, Jupiter.
Precisely. Your mass, the amount of you there is utterly constant. 70 kilograms is 70 kilograms. But here's where it gets interesting, maybe a bit counterintuitive. What about your weight? Is that equally fixed?
Intuitively, my first thought is yes, weight feels constant too.
Yeah.
But I have a sneaking suspicion, based on how you set that up, that our sources are about to, pull the rug out from under that assumption, aren't they? Could there actually be a situation where your weight just vanishes, becomes zero?
That's an incredible question. And yes, absolutely, your weight can become zero. Our deep dive really highlights how different weight is from mass. Weight is not the stuff itself. Weight is the force with which a gravitational body, like the Earth or the Moon, attracts that object, that mass. It's a force measured in newtons and in the SI system, often using a spring balance. And because it depends on gravity, it's not constant. It changes from place to place because the force of gravity varies depending on the planet or moon you're on, or even your altitude. For instance, your weight on the moon would only be about 1/6 of your weight here on Earth because the moon's gravitational pull is much, much weaker. Your mass is the same, but the pull is less.
Okay, so mass is the stuff, weight is the pull on the stuff. And because the pull can change, that leads to the kicker. Unlike mass, weight can actually be zero.
That's exactly right. Your weight would be effectively zero at the very center of the Earth because gravity would be pulling equally in all directions, canceling out. Or, more practically, think about astronauts in an artificial satellite orbiting Earth. They experience weightlessness. It's not because their mass disappears or because gravity disappears entirely up there. It doesn't. But because they are in a constant state of free fall around the Earth. The effect is weightlessness. So, yeah, weight can be zero. Mass cannot. It really drives home how distinct these two concepts are. Mass, amount of substance. Weight, gravitational force acting on that substance.
Wow. Yeah, this whole deep dive has genuinely given us, I think, a new lens to look at the world around us. From realizing our still bodies are actually in constant motion to seeing the subtle dances of mixed motion in everyday objects, it really is all about perspective, isn't it?
It truly is. And if we kind of connect this to the bigger picture, these really basic principles of motion, rest, reference frames, they are the absolute building blocks. They're essential for understanding everything from the vast orbits of planets and galaxies down to the tiniest invisible vibrations of atoms. It definitely raises an important question, I think. How does our perspective, our chosen frame of reference, fundamentally shape how we perceive reality, even in something supposedly objective like physics?
So what did this all mean for you listening right now? Well, maybe the next time you're sitting, feeling perfectly still, just remember you're actually hurtling around the sun at something like 67,000 miles per hour. It's kind of wild. And here's a provocative thought maybe for you to mull over later. What else in your seemingly fixed world, your daily reality, might actually be in constant motion relative to something else you just haven't considered yet? What other perspectives are out there?